Let's just go through this one. All right, we have a circle. And we have points M and N are on circle L. So I'm going to go ahead and I'm going to draw circle L. So this is my M. Those are terrible points, but we got them. M and N. And it says that we have the measure of angle MLN is 60 degrees. So if I connect these, this is going to be, let me put it in red, 60 degrees. Well, if my central angle is 60 degrees, that means my arc is also 60 degrees. On top of that, I also know that the radius is going to be 20. So our radius is 20. So from the center to the edge is 20. Those are the only two things you need to get that arc length, the actual length of it. Not the degree measure, but the length of it. So we're going to jump right to the length of arc. Now this is what I think of length of arc. Length of arc is a distance, right? It's a distance. How long does it take me to walk, or what's the distance from M to N if I'm walking around this circle? Well, distance between 2 points sounds a lot like circumference, right? Because that's the total length around the circle is my circumference. So when I talk about length of arc, you should immediately think of circumference. All right? I'm going to go ahead and write circumference above this. And I want to remember that circumference, the formula for circumference, is going to be 2 pi r. That is the formula for circumference. Well, circumference would be all the way from M to M. I want to walk from M to N, so we know it's going to be shorter than the total circumference. And so what we're going to do is we're going to figure out what is my total circumference and what percentage of my circumference is taken up by this little chunk here. All right? That was the formula we came up with yesterday, which was that length of an arc is going to equal our degree measure, so x degree divided by 360, times our circumference, which was 2 pi r. Well, we know most of this information. We know that the degree measure from M to N is 60, so we're going to do 60 degrees divided by 360 degrees. And we're going to multiply that by 2 pi. Well, my r, we already said my radius was 20. So it's times 20. So 20 times 2 is 40, and then we have 40 times that 60 divided by 360 degrees. And correct me if I'm wrong, but it comes out to something like 6.7 pi. All right, so finding length of an arc can boil down to either memorizing the formula or just recognizing what it is. It's taking your circumference and multiplying by the percent of the circle you're using. Yeah?
I have a different question.
Oh, okay. Is it on the area or is it?
Yeah.
Okay, it's on the area one.
Yeah.
Okay, what's your question on the area one? It might get us the whole answer.
Like, is it just you find the whole area and you just take a sixth of it?
Yeah.
Okay.
So imagine just realize, hey, if my length of my arc is find my circumference, multiply it by the percent of what's being taken up by my sector, right? Because that's this right here is the 60 divided by 360 is how much of our circle is being taken up. We're going to do the exact same thing for area. So in fact, area is almost going to be the exact same formula as this. The only difference is, rather than using circumference, I'm going to use the fact that my area of my entire circle, so that's my entire circle, this is my sector, all right, that's my sector, this is my total area. My total area is going to be pi r squared. Well, to find my sector area, we're going to take our total area and figure out what percent we're using of it. All right, so we're going to do the exact same thing. So my sector area is just going to equal that 60 degrees divided by 360 times, instead of my circumference, I'll multiply it by my area formula. So pi r squared, well my r is 20. Squared. So these two things are interchangeable based upon what we're looking at. And that's why I like to think of length of arc as being circumference, because it tells me, hey, use the circumference. Area we should already know. Use the area formula to find area. We just have to recognize, how do I figure out what percent that is? Okay, so we have 60 divided by 360 times pi times 20 squared. So what I would do in my calculator is do 20 squared. And then I'd multiply that by 60 divided by 360, which comes out to, which is going to come out to 66.7 pi. And because its area is probably going to be units squared, so let's just call it centimeters squared. Let's pretend I gave it units, and I gave it centimeters squared. Well, that means just knowing this one, we know this formula as well. All right, do these two things make sense? Do you have any questions on these? Surprisingly, we're not even supposed to know this yet. This is actually next section. All right, I spent maybe 5 minutes on this right now. But this basically covers what we're going to do tomorrow. So we'll make tomorrow's lesson go pretty quick because we already know it. All right, so that's tomorrow's lesson. It's just basically this. And we're going to add another formula onto it as well. All right, let's go ahead and I'm going to look at 2 homework questions. The first one I'm going to look at is the clock one.
Oh, this was cool.
It is pretty cool.
Like when you figure it out, it's like, what?
Do I not have the right one up? Oh, I think I forgot to switch. There, this is the right one. Okay, it says, what is the measure of the angle formed by the hands of a clock at 10:20? In fact, that's the only question we're trying to answer. I ask a couple of guiding questions after to kind of, that you don't just shortcut it. But we're going to figure out what is the degree measure of the hands of a clock that are at 10:20. What I'm going to do first. What I'm going to do first, and this is going to apply to every single clock, so that's what I'm going to do first. I'm going to create an angle. I'm going to create a big angle. I'll make it out of purple. I'll create a big angle like this. Let's make it a little bit bigger than that. Let's go 8. All right. A circle is 360 degrees, correct?
Yeah.
What is the measure of this angle? It's 90. Yeah, not a trick question. A lot of people are like, 90? Is it? Can I say that? This is 90 degrees. All right, this is 90 degrees. So if this whole thing is 90 degrees, and then I chunk it up into 3 sections. So I started off with 90, and I chunk it off into 3 different sections. Someone raise your hand. Don't shout it out. Think about it. What is the degree measure of each of these chunks? If when added together they equal 90. Yeah. They're each 30 degrees. Yep. So with any clock problem I possibly give you, you should start out with the idea that every hour marker is going to be 30 degrees. All right, every one of these hour markers is 30 degrees. We can start off with that knowledge. All right, because clock problems only have 2 possible problem areas, and this one we're missing one of the problem areas. So we're at 10:20. We're at 10:20, which tells me my minute hand is going to be pointing right at the 4, right? 20, if we know how to tell time. It's not digital. This would be, I don't have the 10 yet. I just have the 20. This is pointing to 4, so this is going to be 30 more degrees, right? Okay. Well, that's 30 degrees. Bless you. So far I have 30, 30, 30, 30. I'm going to have my hour hand pointing. Remember, my hint was it won't be pointing at 10, right? So even though it's 10:20, our hour hand Let's go ahead and do it in blue. Our hour hand isn't going to be pointing right at 10, because that wouldn't make sense. Because as our minute hand moves, so does our hour hand. All right, so that keeps moving. So we know, let's not even think about where it's going to go yet, but our hour hand is going to be pointing somewhere that's not directly at 10. It's somewhere between 10 and 11. Well, that means I can get one more measure. I can get one more easy measure. Because if I connect that to the 11, I still have 30 degrees. So without doing any math, really, not much, just knowing that this is 30 degrees, it's 30 plus 30 plus 30 plus 30 plus 30 plus whatever degree measures here. So I have most of it. This is 150. This is 150 right now, and I have most of the measure. The only hard work I have to do is right here. Well, real quick, let's divide this up into our purple. Let's divide that up into our purple. If I had this entire measure, this would be 30 degrees. That would be 30 degrees. Well, I don't have the whole thing. I just have a part and another part. So now we have to think about my minute hand going all the way down to 4. If it went all the way down to 6, our hour hand would have moved right smack dab in the middle, and I'd have 15 degrees and 15 degrees, right? Does that make sense? If my minute hand went halfway around the clock, that means my hour hand goes halfway between 10 and 11. Did I go halfway around the circle with my minute hand? No. Who knows how far I went around? How far did I go around if I just went to the 4? Sanjeev? We went a third of the way around. We went a third of the way around. And how we figured that out is just take 60, a full 60 minutes, divide by 20, or 20 divided by 60, and that comes out to 1/3 of the way around. All right, so 20 minutes divided by 60. Maybe I'll write some of that down. I didn't really know the class. So 20 divided by 60 is going to equal 1/3 revolution. This went a third of the way around, which means my hour hand moved a third of the way from 10 to 11. So it doesn't look that accurate. I kind of drew it in the middle, but we got to recognize that our drawings aren't perfect. So if this moved a third of the way, what's a third of 30 degrees? 10. So if it moved a third, it means it moved 10 degrees, which means I have 20 degrees on the other side. So that's going to give me 30 plus 30 plus 30 plus 30 plus 30 plus 20, which equals 170 degrees. All right, so your easy part should be this part. The only hard part you should have here is figuring out how far did that hour hand move. Yeah? Yeah. So remember, as our minute hand moves, our hour hand moves with it at a constant rate. Well, my minute hand's at 20. And we came up with the fact that, well, 20 minutes on a clock is actually a third of the way around the clock. So if I had 15 minutes, I would just do 15 divided by 60, whatever fraction that comes up. That's how far my hour hand moved. So if my minute hand moved 1/3 of the way around the clock, that means my hour hand moved a third of the way from 10 to 11. It would have moved halfway. And half would have been easy, right? Because I would have just taken 30 and divided by 2 and been 15 and 15. Unfortunately, this one moved exactly 1/3 revolution. So I just had to figure out what a third of 30 was, and that's 10. So it moved 10 degrees, which means there's 20 more degrees here. Okay, does that make sense how I got that 20? Okay, good. Because this is a really good question. You have to think about a lot of stuff. But the good part about a question like this is you should be able to get almost all of this, and this is the only work you had to do. This is the only real work you had to do. All right, questions on that guy? Does it make sense? Or are we just so confused we don't want to ask a question? We're just tired. It's Tuesday. Okay. The other challenging question was that bridge one. That bridge one, we're going to talk about that one. So all I know is the arch creates a 60-degree arc, and I know the distance of the bridge is 180 meters. They want to know, what is this distance here? Well, just remember that arc length, the length of my arc, let's just put arc down here, is going to equal my degrees over 360 times my, since we're doing length, we're talking about circumference, so that's going to be 2 pi times r. I have 60 degrees, so that means all I need is my radius. I just need one thing. I just need a radius. So if you were on a test, and you want points for this and you're not sure how to do it, you should at least have this written down and say, hey, Mr. Pape, I know this is 60 degrees. I just need to find my radius. I'm not sure how to find my radius. At least I know you know what you're looking for. Okay? So like I said on the test, and I think this last test I had a lot more people write stuff in, which got you more points than if you just didn't write anything in. All right. I gave you that point yesterday that is not a diameter, because if that was a diameter, we'd be done. It is not a diameter because it's just a regular chord that's 180 meters. I need a radius. The easiest way to find a radius is put a point in the middle and connect two radii to whatever drawing you have reaches the edge of the circle. All right? So wherever our chord is, wherever our triangle meets, wherever our square meets, just draw a triangle with two radii. That's how you get your radius. All right, there's two ways to do this now. There's two ways to do this. Well, there's one fact we have to put down. If this is 60 degrees, that means my central angle is also 60 degrees. So that's important to note. Two ways to do this one. First way is the slower way, and that is to say, well, I know I need to create a right triangle. And that would create that triangle where this is 30, 60, 90, where this distance is 90 meters. All right, that would be a 30, 60, 90 with a 90, and we can go ahead and find our radius that way. The easier way, and a little more clever, is to note that if this is 60 degrees, and both these angles must be the same, because the radius goes to the same place, just cutting across, both these angles are the same. This must be 60 degrees. This must be 60 degrees. We have the infamous 60, 60, 60 triangle, which we don't ever call a 60, 60 triangle. We just call it an equilateral triangle. All of our angles are the same, which means all of our sides are the same. So if the base of it's 180, that means all of these are 180. That's 180. This guy's 180. Well, guess what? My radius is now 180. So we can plug everything we need in this equation. So I already have my degree measure. That's 60 degrees divided by 360 times 2 times pi times 180, which you can break down to 60 divided by 360 times 2 times 180 is 360, and it comes out to that 188 point whatever is on the bottom there. What did it actually come out to? 188.5 meters about.
Get that? No, I don't understand.
Which one?
I have all of that, but I got 60 pi. 60 pi equals. Oh, is that?
Yeah. So I should have put the pi in that one. But yeah, whatever this is, because notice how the answer doesn't have pi in it.
Yeah.
So if you take that times pi, then you'll have that 188 point.
Okay.
It's just going between the two forms. That sometimes I'll ask for the exact answer, and sometimes I'll just ask for a rounded answer. If I ask for a rounded answer, that means I don't want pi in it. But on a test, I would accept either answer. All right. So if you factor this down and had pi in it, and in my notebook I had 188.5, I'd just be like, yeah, they're equivalent. All right. So don't worry too much about which one I'm looking for, unless I like bold and say gear towards giving exact answers. All right, so I actually like your answer better than what I put on there, because I gave an approximate. But more often than not, I'm going to ask you for exact answers. Okay? All right, do we have other questions on the homework? Going once. Going twice, Grace. Number 12. All right, number 12. The big thing about number 12 is we have a length of 15 pi. That was the trick to this one. So we have a length of 15 pi. So from T to V is 15 pi. Some people thought it was a chord. It's not a chord. It's the whole arc. So the length of the arc is 15 pi. As soon as I hear length of arc, I'm going to go ahead and make that. I'm going to say, well, okay, all right, Miss Pavement, I got you. I'm just going to put my length formula down. All right, I'm going to put my length formula down is x degrees over 360 degrees times 2 pi r. Because I know you're going to want that. You asked for length of an arc, I'm going to use the length arc formula before I even read anything else. Well, the length of the arc is already 15 pi, so I know the length is 15 pi. Equals, hey, wait a minute. They give me an inscribed angle of 75 degrees. That means from here to here is going to be 150 degrees, right? Because we double it because it's inscribed. 150 degrees, so that means I have my x value. I have 150 divided by 360 times 2 pi r. Now I have an entire equation where I just have r sitting there. All right, so you just do the 150 divided by 360 times 2, 15 divided by that, and your pi's are going to cancel out, right, when I move this over, and you'll come up with your answer from there. Okay?
Yep.
All right, other questions? So like I said, if you're ever stuck on something, write down what equation you think I'm looking for. Because sometimes that's all you need to plug information in. All right? And if you get stuck saying, Mr. Bailey, I know I need to use this formula, I'm not quite sure how. All right? So if I talk about lengths of arcs, you should immediately think of this and maybe even write it down. Okay? Then we're going to go into today's lesson. Okay, really quick. Oop, that's got all this stuff already in it. How? Okay, quickly. Who can give me the circumference formula if I'm given a radius? And I just want to use the radius. Mazen. 2 pi r. All right, what if I'm given the diameter, but I still want to find the circumference and I don't want to put it in radius form? Ooh. Yeah. Pi times diameter. All right, how do I find the area of a circle if I'm given the radius? This class just is not full of volunteers today. Yeah. Pi r squared. And finally, what if I'm given diameter? This is the hardest of all of them. And it's not that hard. Someone new. Whew. I'm just going to be sitting here all day. Yep, pi times diameter divided by 2 squared. In other words, if your diameter is 10, half it to 5, which actually gets you your radius. All right, so really it's the same formula. It's just our radius is diameter divided by 2. All right, those are all our major formulas. All right, so we have area equals 28 pi centimeters squared. It says solve for r. So the first thing I'm going to note is, hey, area equals pi r squared. Well, pi r squared is my formula, and my area equals 28 pi. So that means pi r squared is going to equal 28 pi. The first thing I'm going to do is I'm going to get that pi out of there by dividing both sides by pi. They just turn to 1. And so we have r squared equals 28. We're going to go ahead and take the square root of both sides. And we're just going to have r equals the square root of 28. What is a perfect square that goes into 28? 4 goes into it. How many times does 4 go into it? 7 times. So we can rewrite this as square root of 4 times 7, which is going to equal to square root of 7. My radius is 2 square root of 7. Once again, it just involved me writing the equation. And that was my starting off point. All right, if r equals 3 over 8, find the area. I'm going to skip that one. It's just plugging into the formula because area is pi r squared. Just going to plug 3/8 in for r. I just want to get to this one. I want to make sure we have time to get through this one. I just want to get through some terminology and how we solve a problem like this. All right, a circle is circumscribed about an equilateral triangle. So just using context clues, even if we're not sure what circumscribed is, it says about an equilateral triangle. So that means there's a circle going around an equilateral triangle. Oh, you were going to tell me. Okay. The easiest way to draw these is to draw your circle first. And then, I don't want it that much. 2 is fine. And then just kind of draw kind of an equilateral triangle. I'm limited by my snap grid. It doesn't always like. Kind of an equilateral triangle. But as soon as I put each side is 18 centimeters, it becomes equilateral no matter how crappy the drawing is. So this is 18. This is 18. This is 18. What is the area between the circle and the triangle? That means I need to find two areas. I need to find the area of the triangle. I need to find the area of the circle. Because as soon as I find the area of the circle and I subtract out that triangle, that will be the area in between. So we're looking for this area, right? This shaded stuff. I see a lot of people already have it drawn, but I'm looking for that little area there that's between the two. Which means it's the circle minus the triangle. Let's start with the triangle. So let's do triangle area. So we're going to do the area of the triangle. Remember that the area of a triangle is half our base times our height. We have our base. We just need to find our height. Well, what I'm going to do is, and you don't have to, you could do it within there. I'm just going to redraw the triangle down here. So I'm not doing too much work inside of there. So I got my triangle. Just brought it out just so I could say, well, I'm looking for this guy, this height right here. And it divides it in half, so this is 9, this is 9, this is 18, this is 18. Well, it's a right triangle, so we could use trig if we didn't recognize something. This is an equilateral triangle. What are the degree measures of every single angle in an equilateral triangle? 60. So we got 60, 60, 60. That means that this angle is 60, this is 90, so this must be a 30, 60, 90 degree triangle. A 30, 60, 90 triangle. The one across from 30, so the one across from 30 is going to be our S. So S equals 9. The one across from our 90 degrees is going to be 2S. Yeah, 2 times 9 is 18. That one's good. All right, then our height is going to be our S square root of 3. Well, my S is 9, so maybe I'll just write that off to the side. Hey, H equals S square root of 3. My S is 9, so my H equals 9 square root of 3. So the area of my triangle is going to equal half my base, which is 18, times that 9 square root of 3. Half of 18 is 9. 9 times 9 is 81. So the area equals 81 square root of 3. Cool. Triangle done. Check. The only other area I have to find is the circle. So like I said, if I'm looking for circle area, I'm going to write down what formula I'm going to use. So my circle equals or the area for my circle is going to equal pi r squared. Pi is just a number, so I just need to find my radius, and I am done. I just need to find a radius, and I am done. And Nicholas has a good idea right there. Yeah, Matthew.
Can I say it?
Are you going to say what to do?
Yeah.
Yeah, sure.
So if it's circumscribed, then the distance of the center of the triangle to each vertex is the same.
Mm-hmm.
So you could just make you could like draw each vertex to the center, and that makes 3 equilateral triangles, and then you can just find the distance of one of the vertices to the center. And that's the radius.
Okay, there's one change I would make. So what Mazen's saying is, I assume this is what you're saying, is you just take a point here and you note that this would be a radius, and that would be a radius, right? This doesn't create an equilateral triangle, though.
I mean, isosceles.
Yeah, isosceles triangle. Okay. All right. So do we all see what happened here? That I just find a point in the middle of my circle, and we know that any line that I draw from here to any one of my vertices is going to be a radius. But if I draw 2 of them, it creates a triangle, and this is going to work every single time. This is how we solve those n-gons, right, or polygons. Is one of our big steps was put a point in the middle and connect 2 vertices. That's going to get us our radius. All right. The other important fact about this is, can someone tell me how to find the degree measure of this? I need to know what degree measure this is in order to help me solve this triangle. We did it with n-gons. Fritz, do you remember? I'll give you a hint. There's 3 sides to a triangle. It has to do with 3. How many degrees are in a circle? 360. Now I have 3 sides, or 3 angles, right? So I can create 3 angles. Just like Matt said, I can create 3 angles. 1, 2, 3. I got 360, so what do I do, Grace?
Well, since the ones split the 60 degrees in half into a big triangle, it would be 30 degrees.
Yeah. So Grace was saying, well, let's just look at this. I split this in half, so this is 30 and 30. That's a good way to look at it. How do I get this central angle? And you got there, because this is 30, 30, so this must be 120. What's a quicker way to get to the 120? Or, doesn't matter what shape we have. If I have 3 sides, I create 3 angles. How do I get what that central angle is? We just did it. We took a test on it. Haley? 360 divided by 3. 360 divided by 3. Because if this is 360 degree triangle, and I create 3 angles, right? I have 3 angles, 1, 2, 3. I just take 360 divided by 3, and each of those is going to be 120 degrees. So Grace, your thing worked, but this is the only example it would work in. Because if I had, I don't know, a pentagon, it would no longer divide it in half. It just happened that it worked on this one, that it does divide in half. An easier way is just draw your 2 things. Your central angle is 360 divided by the number of sides. All right? You do need to know that. All right, so 360 divided by 3 is 120. I'm going to redraw that triangle because I'm going to do some work on it. So I'm redrawing that triangle. We said that this angle is 120 degrees, but if I draw a right triangle, because that's always our goal to have right triangles, it means that this is a 60, and Grace was right that this is 30, 90 degree. The base is 18, so that means that this is 9. So our base is, I split my base in half, so it's 9 and 9. Now just remember, for a 30, 60, 90 degree triangle, the one across from 30 is our S. So I'm going to write an S, the one across from 30. The one across from 90 is 2S, so our hypotenuse is 2S. And the one across from 60 is going to be our S square root of 3. So our s square root of 3 equals 9. I also want to note our hypotenuse is also our radius. Right? Our hypotenuse is our radius. So once I solve for s, I have my radius. Alright, s square root of 3 equals 9. Let's go ahead and do that work off to the side. So I have s squared of 3 equals 9. I just need to solve for s. I would divide both sides by square root of 3, so I'd come up with s equals 9 divided by square root of 3. I can't have square root of 3 in the bottom, so I'm going to multiply the bottom and top by square root of 3. That's going to equal 9 square root of 3 over 3. Okay, so we have 9 square root of 3 over 3, which is just going to equal 3 square root of 3. So s equals 3 square root of 3. So 2s, 2 times that is going to equal, 2 times 3 is 9. No, it's not, it's 6. Whew. What was that? Jack, do you have a question? Oh, okay. I was wondering if I made a mistake. No, okay. So we're all clear on how I got this. Alright, so 30, 60, 90, right? We have to know those. We have to know those. Alright, so 6 square root of 3 is my 2s, which is also my radius. So I pull this triangle out. It's my radius. So that means the area of my circle is going to equal pi times my radius. Well, my radius was that 6 square root of 3 squared. I'm going to kind of work it down. So we're going to have equals pi times 6 times 6 is 36. Square root of 3 times square root of 3 is 3. So my A is going to equal 108 pi. I got my area of my circle. I got the area of my triangle. To get the area of that between area. So area between that's going to be the area of our circle, which is 108 pi, minus the area of my triangle, which is 81 square root of 3, and that's how we're going to leave it. They're not all going to be this tough. Some are going to be like squares, and squares we just have to find diagonals. Alright, so if this was a square inscribed here, I would just say, well, my diagonals here creates a right triangle. Wouldn't be hard to go from there. Okay? But this is basically a baseline for how you do things with polynomials and finding areas inside of a circle. It's to put the point in the middle of your circle, connect two vertices, and if it creates a 30, 60, 90, or a 45, 45, 90, use those facts, otherwise you have to use trig. Okay? Alright everyone, your homework is just that worksheet that's attached to it. Alright, the answers are on the bottom. I might put an answer key up tonight so you can check. I haven't decided if I'm going to or not. Just because some of these are tougher problems. Alright everyone, have a lovely, lovely Tuesday.